Okay, I'm going to start now formally. I'm Marcia Meskimen. I'm the director of the Institute of Advanced Studies, and it is my absolute pleasure today to be welcoming everyone who is joining us virtually, but also here at International House, as this is a hybrid format, and we are really looking forward to today's discussion by our visiting fellow, Mark Ehsani, a visiting fellow we have been waiting for some considerable time, because this is very much also a visit that had a long period of intercession from pandemic and so on, and we are very, very thrilled at last to be in the room with and ready to have a conversation with Mark after the event. The IAS, as everyone knows who is tuning in, I'm sure, is the hub at the university for international visiting fellows, and through it we have a whole range of wonderful collaborative projects across every area in the institution. And one of the things that we really value about the IAS in terms of its international fellowship program and in terms of its ability to bring people to Loughborough is the fact that we have dialogues across disciplines, and we have dialogues on some of the most important issues of the day, pressing and core issues facing all of us. Today's talk is going to prove, I'm sure, to be absolutely part and parcel of that kind of dialogue and discourse, inviting colleagues from a range of different fields to have a real discussion and debate about core issues to do with global geopolitics, to do with Green New Deal, to do with how we use technology, what technology means, and how creative thinking actually needs to be part and parcel of what we value and what we push forward into the future. With that said, I'm going to stop the part of the IAS introductions and turn over to my colleague Canvas Ibrahimi, who's going to do a brief introduction to Mark's work here and the visit, and then we're going to welcome Mark. So very much welcome to all, and we're looking forward to this.
Yeah. Hi, I'm going to introduce you to Professor Mark Ehsani. He's a professor of electrical engineering and director of sustainable energy and vehicle engineering research program. Also, he's director of the power electronics and motor drives laboratory at Texas A&M University. Mark has been honored by various international organizations, including IEEE, Vehicular Technology Society, Avant-Garde Award. He's the co-author, and he has over 450 publications, 21 books, and over 30 US and EU patents. He's been a consultant to over 60 international companies and government agencies. He's very well known for his work on the electric vehicle and hybrid electric vehicles. Since 2000, he was one of the main consultants to US government on the electric vehicles. Thank you very much, Marcia. I'll pass on to
Okay, let's do that. Perfect. Good to go. Thank you very much for this kind introduction and the welcoming and everything that you did today. I feel so honored that I can't wait to see what I have to say today to be worthy of this introduction. The subject of global warming and sustainable energy and its correlation with transportation and vehicle technology is extremely broad and can be extremely deep technologically. And when you add the word global perspective to that, it's virtually all on everything that is relevant to our survival and the subject of the day today. So I'm going to try to make at least give a some perspectives on this. I'm going to try to avoid the temptation to get too deep into the details of technology unless absolutely necessary. I hope that the takeout from this presentation will be that we have not quite got our arms around the subject of global warming and its causes. And when a problem is not well defined, all the solutions are either ineffective or counterproductive or feel-good attempts. And so that's one of the things I want to emphasize, to understand exactly how global warming is happening and what are its, both in time and in terms of its component drivers. And then review some of the current attempted solutions and plans and perspectives and show their inadequacy and sometimes counterproductiveness. And then give some small case study examples of successful definition of the problem and attempts at the solution. Although they're microscopic, you know, the journey of 1,000 miles starts with the first step, but the first step in the right direction. So the big theme is that global warming is a planetary problem. It's global. Therefore, our perspective and our solutions should also be addressing it globally. All right, that's easy to get. It also happens that nearly 90% of the world population is technologically, socially, and economically underdeveloped. They are going to be, and progressively are, the main drivers of global warming. It is not the fact that the 10% of the world population in Europe and North America, which are technically more developed, are going to, by changing their behavior, are going to remedy or slow down the process of global warming. Therefore, one of the takeouts from this thing is, do we want to solve the 10% problem, how to behave correctly in the developed world, or do we want to solve the 90% problem? I think the answer is suggested by the question. And then if we are convinced of that, exactly what is the strategy? And again, the takeout, I'll take you to takeout. I'll give you the takeout so that in case you want to get up and go do more important things. The solution is for the developed world to get in there ahead of everything else and develop the developing world technologically and economically according to sustainable low carbon emission strategies and technologies, and do that based on appropriate technology, not advanced technology, appropriate technology, appropriate to geography and to sociology of individual locations, and do it with sustainable motives, which is sound business principles and models. Not do good, not affirmative action, not charity, but good business plan. And to paraphrase, one could say to have a Marshall Plan for the world, to develop the world clean and quick. And I'll show you if we don't do that, what are the consequences? And what about the 10% that seem to be consuming all the fuel and producing, you know, converting fossil fuels to energy and using it? As you'll see, the best strategy immediately for the developed world suggests itself to be improve the efficiency of consumption. We can very quickly actually reduce our efficiency of energy to service or energy to value conversion by 50% using advanced technology. And in fact, have better services, better value, better products, less energy consumption, and therefore less emission. And the magnitude of our emissions, which is large in the developed world, can reduce faster with efficiency improvement rather than trying to go zero emission per se, solar energy per se. And I'll show you that this is not actually a choice, it's observing what's on the ground at which we are neglecting. So having given you the punchline, let's excuse this, it's not meant to be readable, but as I woke up this morning, I was reading the news and this popped up. And I thought it's good to see that Elon Musk says that fossil fuels are one strategy, basically fossil fuels are here to stay for us in the developed world, and we should use it wisely and not think about giving it up immediately because it's meaningless. I didn't have time to cull through it, but he actually says electric vehicles have limited immediate impact in the developed world. And he's the greatest manufacturer and seller and promoter of electric vehicles. So even those who we take to be the leaders of zero emission in transportation are trying to give us a sense of perspective. But this is such an ugly slide that I won't waste too much of your time on it. Some trends and background information. As you know, the world population has been growing, at least in my lifetime, by a factor of 3, and it's expected to taper off to about 9-point-something billion people. And our current power demand is about 15 terawatts. And what is terawatts exactly? If you're not a technical person, a tera is a difficult number to imagine anyway, but 15 terawatts is 15,000 gigawatts. And what is a gigawatt? A gigawatt is the electric power generation capacity of a very large nuclear power plant. So we're talking about 15,000 large nuclear power plants. That's what the world is consuming. And this will grow by some 30% or so by 2035. Now, if you look at the current picture of energy production in the world, 85% of it is from fossil fuels in the form of coal, oil, natural gas. And these so-called promising technologies that are supposed to save us are currently in a very small minority. And there are reasons for that. Global warming is primarily due to carbon dioxide emissions from fossil fuels. Some of it is from methanes and nitrous oxides and other industrial activities. But primarily, again, always solve the 90% problem, not the 10% problem. It seems to be an easy thing to teach our kids. Of the carbon dioxide emitters on the right side of this slide, it has a current percentage of for electrical production, agricultural activities and deforestation, buildings and use of concrete, which is a very energy intensive material production, transportation, automobiles and surface transportation, which happens to be one of my technical interests, and then industrial manufacturing products and what have you. There was something about this I wanted to mention to you, see if I can remember it. I can't remember right now, but anyway, moving on. First of all, fortunately or unfortunately, there's no limitation to hydrocarbon resources on the planet Earth, which technologically is recoverable and usable by us. So we are perfectly equipped and well motivated to destroy our planet by carbon emission, because we have approximately 500 exajoules of hydrocarbon fuels accessible to us, which at the rate of 0.5 exajoules of consumption per year currently, we have 1,000 years of hydrocarbon fuels available. So we are not going to get out of Stone Age because we run out of stones. It's going to be some other motivation. And in fact, hydrocarbons are in the form of methanes, equitably distributed all over the world. Extraction of them could be suicidal, but I think this is singing to the choir. Now we know that we have no shortage of energy. In fact, even if you talk about nuclear power, we have about 9,000 years of recoverable uranium accessible to us. We are going to run out of cheap uranium, but we have uranium available to us. And considering that uranium is only 0.2 cents of the cost of each kilowatt hour of electricity, even if it goes up by a factor of 10, it's going to be a small fraction incremental increase in the price of electricity. That's why we have lots of nuclear power. In fact, that article that I abstracted, Elon Musk is very encouraged about nuclear power. And, you know, we can have mixed feelings depending on our depth of understanding about, is nuclear power safe or isn't it? It is a system of unstable equilibrium. It's like making a stick stand on your finger. You can make it stand there, but it's unstable, but you can make it stand. So is that dangerous? Are we in the, well, if you ask the question at a logical level, the answer is no, it's not dangerous at all, because airplanes are also in a state of unstable equilibrium. They want to fall and crash unless we do it right. The power plant, the pilot control, and everything else. And there are perturbations and storms and winds and this and that, and lightning and fronts and what have you. But somehow we managed to do this. In fact, as I was coming across the Atlantic, just whimsically I asked myself, what is the possibility that I'm not going to make it to the UK? And I've got a lot of good work left behind that I need to do. And I realized that I don't know of a single airplane flight failure in history across the Atlantic. No airplane has ever crashed to my knowledge, and maybe it never did. If that's unstable equilibrium, controllable and made safe by man and good engineering, I'll take it. There was one, but that was, I'll talk about that. That was actually a missile attack on a passenger airplane. Which brings me to the second topic. Yes, nuclear power is emission-free and clean, both in its fuel excavation and fuel management and spent fuel management and all those things. But if it becomes a hostage of warfare, now it's a whole different story. And this notion really came to me empirically after this current war in Europe, that a nuclear power plant has become a hostage. And if it was made to be stable and successful, just like an airplane, but it wasn't made to be missile proof and destruction proof and war proof. And so that's a different kind of vulnerability, which is a weird one, because it's a mutually assured destruction type of threat. We can poison Europe both on the side of the perpetrators and victims. You know, so but it can force change of behavior, which is not a good way to do diplomacy. So there are issues about that, but we have a lot of energy, both emittable and non-emittable type of energy in terms of greenhouse gases. Of course, in the US, we are very blessed with 300 years of coal. We will never go hungry or cold, and the price of energy will not go out of control. We've got it. Natural gas, oil, the US alone, or by extension, our better neighbor to the north combined. And of course, in addition to the fact that the US is blessed with all kinds of natural natural resources of energy and other fundamental things, having that kind of a heft and weight in the market, we can control, we can be a force of good about manipulation of energy and prices and what have you. But we're talking about the 10%. The fact of the matter is that 90% of the world population living in China, India, I've already spoken about, what, 2/3 of the population of the world, plus Southeast Asia and Africa and so on. These are countries that are not developed. And this is what happens. If you look at, I can't point to this, or can I? Yeah. If you look at the current picture, and this is the work of one of my graduate students out of my graduate class, actually. He gets credit and I get to use it. Currently, the CO2 emissions by this particular source's estimate is about 35 billion tons per year. And look at the contribution of Europe and North America and everything else combined, which is 10 billion. This is still the 90% of the world population being undeveloped by the developed world standards. And look at their contribution from 10 billion to 35 billion today. There's China, and look at India. India hasn't even begun to blossom yet. It is a potential both for good and harm in terms of ecology yet to be fulfilled. So this slight decline that you see is not coming from the 90%. It's coming from the bending of the curve of the 10%. And believe it or not, most of that is happening because of efficiency improvements and not because we switched to non-emitting sources of energy. So if you want to solve this problem, of course, the trend is going to grow. If you want to solve this problem, what is the problem to solve? The advanced world or the developing world? That's the theme of this talk, basically. Put another way, here is the this is the carbon dioxide emitting nations. The developed world, 10% is emitting 35%, and the 90% is emitting the 63%. This ratio is going to change, both naturally and, in fact, by our misconceived ideas about doing good. And I'll show you that. There are lots of arguments to be given, but let me kind of put it in a summary. In the developed world, we have vested capital, and we have existing plants that have to go through their lifetime. A power plant has a lifetime of 30 to 40 years. And even if you wish well, you cannot scrap a power plant. It has to go through its lifetime because it has to pay for its cost according to business models. So the long time constants for things to turn around. But most importantly, and this is the, what do you call it, negative feedback or positive feedback effect. Oil is a fungible commodity. If you don't consume it, somebody else will. In fact, it's more than that. If the developed world, which is responsible for the consumption of virtually all of the hydrocarbon fuels, such as oil, if we stop using it, the price of oil will sharply decline, get close to its cost, and its cost is very low, cost of excavation, $5 in the oil-rich countries per barrel. What happens when the price of oil goes from $100 approaching $5? Now the 90% of the world population can afford to immediately start consuming this thing, however wastefully, to quickly develop economically and technologically and socially, just like we did in the developed world from the advent of industrial revolution, founded in the UK itself, with the abundance of coal and easy access to it, and therefore aggressive use of coal. And then it became amplified with the discovery of liquid oil and use of oil. So oil and coal were the fuel or the lifeblood of explosive growth of technology, industry, economy, and standard of living of the West, if you will, or the developed world. Well, if the price of oil approaches its production cost, it's going to happen to the developed world. In fact, it's even worse than that, because if I can think of this, and I'm not an oil salesman, I think that those whose lives depend on selling oil can think of this. I hope they'll turn it off and don't listen to this, because I'm going to tell you what they're going to do. They're going to do what Kodak Film Company did when there was a threat of film going obsolete. They would give away the camera for free or virtually for free, so that now you're committed to using film because you want to use this good gadget that you got for free. Great cameras. My grandfather gave me a Instamatic camera. I loved it. I used it so much. And of course, I increased the profits of Kodak Company. Okay, that may be a little bit too much ancient history for some of the newcomers, less than 70 years old. Let's talk about the printers, the desk printers. In the US, I don't know how the picture is here, you can buy a desk printer for $80. It's almost a giveaway, but it demands about $80 of ink cartridge every year. So they give you the printer, and now you're on the hook to consume the consumable, and that's where the profits are. In fact, the printer I bought came with a cartridge, and I didn't use it. And then when I tried to use it after a year, it says, this cartridge is out of date. If you use it, you are risking destroying your printer. And I got tricked. I didn't want to ruin my printer. It's an $80 printer. But somehow psychologically, because I felt smart when I bought it, now I feel smart by spending $80 more and using what I didn't use to protect my, so you get the idea. So here is the way the model translates. A country like Saudi Arabia, from where I have brilliant students currently and in the recent past working with me for their PhDs, can go to India, China, well, maybe not China, but Africa or Southeast Asia, and say, we will build oil-based electric power plants for you for free. Furthermore, you don't have to pay us for the fuel either for the next 30 years. We will just take a percentage of the proceeds of the sale of electricity. What developing country can refuse such an offer? Because electricity is the foundation of technological, economic, and social growth. Everything, education, manufacturing, everything depends on electricity. So their economy grows, they pay for their electricity, and some of that pays for the initial cost and the cumulative cost of operation. It is actually doing good for the world, except who suffers through this good act of mutual benefit? Planet Earth. That's the problem. So this idea of the developed world getting off the consumption of hydrocarbon fuels, in my mind, is a white elephant. It's a fallacy. It's counterproductive. At least we need to conceive problems in a global way and in a consequential way. So, we in the West, or in the developed countries, in order to save planet Earth, should quickly go and develop the rest of the world, bring them up to an acceptable standard, whatever it is, every family having a personal transportation, not necessarily a 8-cylinder BMW X M series with 700 horsepower necessarily, but the minimum, independence of individual transportation and everything else. We should go in there and do it based on profit motive, sound business models, appropriate technology, and before the oil men get there, and do it for free. That's the idea. And this idea, and I actually teach this to my both undergraduate, especially graduate classes, that we teach you advanced technology and we test you for advanced technology mastery before you can graduate. But really, the smartest thing is appropriate technology. After having learned advanced technology, you should not be so enamored or infatuated with it that you apply to every problem. Elementary problem need elementary solutions, not advanced solutions. Appropriate technology takes higher level of competence, wisdom, and intelligence than advanced technology. Everybody knows engineers are bookworms and kind of narrow-minded, such as myself. But exactly how to apply this focused skill is very important. Appropriate means locally appropriate. Locally appropriate renewable technologies. I'll give you an example from my personal experience with the country of Panama, where I've had several brilliant PhD students go back and become professors and government high officials in the area of energy. And they asked me to come in and work with their government and their top university and the faculty to come up with a national strategy for energy production, technological development, and reducing emissions. And I spent a lot of time in Panama studying the culture, the geography, the economy, the industry. I mean, they are using bunker oil, which is the dirtiest form of hydrocarbon fuel, in diesel engines to make electricity for their national grid. That is their picture of their electric power grid technology. And that's 70 years ago in a developing country. I used to see that when I was growing up. And the emission of that and the pollution, local pollution and health hazards of such a thing. And yet, when I visited Panama Canal, I realized Panama Canal runs on passive energy. There are no pumps or use of energy to lift these gigantic ocean liners from one side of the continent to the other over the mountain. They do it purely passively. They have reservoirs of water from the rain in yet higher elevations, and by basically opening valves and discharging these high elevation waters into different level locks, they lift the ships up and then they lower them down. Everything is done by solar power, the power of rain and sun and rain. And this was done over 100 years ago by some genius American engineers. And I thought, there is the inspiration. So I looked at that, and it turns out this little country is extremely well endowed with hydropower. Lots of mountains, lots of unutilized reservoirs, which can be used for storage of water at high elevation, which means energy, solar energy. And they have wind power because of their mountainous cross-oceanic location. Tremendous seasonal winds blow from one side, from Atlantic to the Pacific and back and forth. I had a PhD student work on this. How do you hybridize wind power, which is a little stochastic and doesn't follow the load, with hydropower, which can follow the load to satisfy the local need? And then this, when you do the calculation, this huge abundance of renewable energy source they have, I came up with a little idea for them. I said, think about Panama becoming the server farm capital of North America. So you may or may not know, but server farms that support the internet and these distractions, they are responsible for in excess of 15%, approaching 20% of electrical power consumption in the United States. And the picture is going to become a lot worse because there's this new thing being developed called the Bitcoin, the cryptocurrency, which is extremely energy intensive, and it produces imagination, which people consider a store of value. In the US, we have 1.2 gigawatts of power consumed for Bitcoin mining, which means feeding the computers, which are basically space heaters, that's what they are, to produce some rare numbers in the name of the owner, which is called Bitcoin in a ledger, and that person can trade that. 1.2 gigawatt is like all the power consumption of the huge city of Houston, or a gigantic nuclear power plant. All that power. So the point is, you know, this kind of power consumption by the internet and the cyber world is extremely CO2 emitting, because look at the picture of energy production in the US. It's primarily hydrocarbon fuels. And they are trying desperately to either not be CO2 emitting for their server farms or appear not to be. So both the public relations and substantially, they're trying to do it unsuccessfully. But Panama, with excess natural renewable power, could do this. And the shipment of data back to the US is much easier than shipment of goods and raw materials. So it seems to be a fantastic. So I can't tell you if they're following that or not. That's another presentation, classified presentation. But it's a very good example of appropriate technology. We must understand the vicissitudes or the specifics of the people and the geography and everything else before we try to do sustainable energy for different peoples of the world, different regions. But that's the type of things that need to be done. Again, these are strategies for 90% solution. This is something that I learned, in fact, in one of my previous trips in the UK. I was giving a talk at Cambridge, and these very dynamic, handsome fellows after my talk pulled me aside and said, let us show you something. These people are building solar power sources, basically lanterns run by the sun. It's a solar collector, a battery, and an LED light source, which collects solar energy during the day, stores it at night. It lights up different huts and you know, village homes in the developing world, and their target specifically at that time was African villagers, because these people actually use dung and wood and kerosene for their lighting. I'm very familiar with that. I studied first grade under the light of kerosene. It's not fun. Not only is it a fire hazard, but it's a significant motivator of respiratory problems and death for children and in the developing world. This idea of using kerosene and these kinds of things. These people at that time produced these devices for $50. They would sell it to these villagers with $10 upfront, and then the rest of the money would come by them displacing the kerosene annual budget of the family. You know, they say whatever kerosene you paid for, you pay us annually until you amortize the cost of this into $50. I thought, and they were doing a great job at that time. This is 5-6 years ago. They had 21,000 customers in Africa. They're doing this to make money. They're good businessmen. They're not going to become billionaires, but they were happy, both financially and spiritually. They were, and look at the model. They jumped in there before the national grid was there, before some NGO got in there and tried to do donations and do good. And they did it with local resources, which is the sunshine and what have you, solve the problem. Those people gave up kerosene to buy solar energy, to have better service and make somebody money. Microscopic example, but this is what appropriate technology means. It comes from smart people. And there are other companies that do these things. We did a project with Saudi Arabia. I had a brilliant Saudi Arabian student who insisted in doing a PhD with me. I thought, what do you need a PhD for? Just go in there and become a recipient of this fantastic income for the rest of your life. But he wanted to do it, so I gave him an impossible project, and he did it. I said, show me how Saudi Arabia can become a non-CO2 emitting country. And he did. And how do you integrate the renewable power source for Saudi Arabia into the current grid of Saudi Arabia? And how do you do it technologically and on sound business practices? And he came up with this idea that we did together, and he did all the math and optimization and simulations. Naturally, I can't do math, and that was for PhD. Saudi Arabia, to use example numbers, because I don't know the exact numbers, produces oil at $5 a barrel. They sell it at $100 a barrel, but they consume it at $5 a barrel because it's an internal product, and it's a national grid under the control of the same government that produces oil. Should they, well, that's one side of the economic story. And the other one is there a second gigantic, virtually infinite resource of energy in Saudi Arabia? Yes, it's called the sunshine. They have enormous amount of surface area, and they have enormous amount of sun most of the year, with very little perturbation like rain involved. So they could actually displace their oil-based electric power generation with solar power panels, as expensive, capital intensive and service cost intensive as it may be. It can be paid for by the cost differential between not consuming oil at $5 and selling it at $100. So it can pay for itself much shorter than the lifetime of the solar power plant or solar farm. And of course, it turns out that it's even better than that, because 60% of electric power in Saudi Arabia at that time is consumed for desalination of water. So they burn oil to make water to drink, if you will. And now, water happens to be a perfect storage product. You don't have to, you see, solar energy, solar power does not track electric power demand. The sun shines during the day. Most of electric consumption is at night when people come home or in the morning. And for that, you need to have energy storage, which is a very technologically problematic issue, both cost-wise and other things, which I don't want to share with you in international public forum. But I've been to many totally destroyed large battery storage farms in Hawaii and other places. I've seen the causes, I've studied them. Energy storage from solar and wind is really not a technological, it's an inappropriate advanced technology. But value storage, store the thing that electricity is used for if it's possible. If it's water is energy intensive, it can be stored. Aluminum, some of the other energy intensive. So you can store value that electricity is used for. And so in this case, they can store water easily and use it when it's needed. Water will balance, will even the imbalance between the electric power production and the consumption. So it's just a fantastic solution. Now, you can look at it two ways. Our Saudi Arabians are going to therefore sell even more oil to the rest of the world, Not if we're working on the other side of the problem too. Get into the Africa and take care of that hut and that village and that province and create a microgrid, and then connect these microgrids together and produce a local grid and eventually a national grid renewably. So we can work on that side of the problem that way. And then are we working against Saudi Arabians? No. They can have their national resource last longer. Instead of 40 years of reserves left in Saudi Arabia, you didn't hear that from me. It's an example, okay? Forget it. It could be 100 years. So they have a longer access to their national income. Gives you an example of the type of strategies to get your mind around the problem and not be committed to glamorous short-term or self-advancing solutions. So I think hopefully you get the picture, although through a keyhole, of how to address the problem of the 90% of the world population. People with technical smarts and with money should jump in there and take care of our underdeveloped brothers and sisters and bring mankind to an acceptable level of development and dignity and parity, and in the process save the world and make money. What about the developing world, developed world? Let's work on efficiency. The point is efficiency can be improved at a much shorter time constant in a much shorter period than lifetime of a hydrocarbon power plant, which cannot be squeezed and it cannot be decommissioned before its lifetime for economic reasons. So let's address transportation. There are fundamental problems with electric vehicles displacing conventional hydrocarbon fueled vehicles. There are fundamental problems based on physics that cannot be wished away or legislated away. For example, liquid hydrocarbon fuel is ideal for transportation because transportation requires lightweight, compactness, safety, and so on and so forth. That's exactly what liquid hydrocarbons do. And the most important thing is when you carry liquid hydrocarbon fuel, you're only carrying half of the fuel. That's why it's so light. The other half is oxygen, and it comes for free everywhere you are. You carry the fuel, but the oxidant, you suck it out of air. That is a solution specifically designed for the planet Earth. It doesn't apply to the moon or Mars. Transportation has to be electrified over there, but not on this planet. That's what, and by the way, how do I know that? Because virtually everything that moves on the planet Earth runs on hydrocarbon fuel. Earthworms, professors, giraffes, and everything in between. With few exceptions of some creatures in the bottom of deep oceans near the tectonic geysers and what have you. Those things actually don't run on oxygen, but they don't make decisions. We do. We published a paper in the early 90s showing that there are fundamental limits to the range and performance of electric vehicles of any kind relative to hydrocarbon fuels. So an internal combustion engine plus hydrocarbon fuel will always be superior to an electric vehicle. The battery that could make this happen is impossible if we extract the elements of that battery out of the periodic table of elements. And the details of that I will not elaborate too much here. But here are some fundamentals of that. If you look at the energy density per weight and volume of hydrogen, lithium-ion batteries compared to gasoline and diesel oil, the density per weight and volume is a factor of 100. A kilogram of battery, the best battery, has 1% of the energy concentration of 1 kilogram of gasoline. That's very difficult to overcome. even if you come up, this is what we did, this is what professors do, they look for theoretical limits, you know, what is possible? Occasionally we get surprised because there's this joke that, yes, it works in practice, but what about in theory? But you know, we want to know what is possible in practice. And lithium-ion batteries, although I'm not an electrochemist, is not too far from close to ideal, maybe by a factor of 4, from the best that you can do with the most electropositive element of periodic table, which I believe is aluminum, and the most electronegative element of periodic table. And if you make a ideal battery out of that with ideal electrolyte, notwithstanding the necessities of the containment and electrodes and support structure, you cannot get anywhere close to overcoming a factor of 100 difference. Furthermore, this is in practice, when you put fuel in your car, you are charging your little gas tank in the car at the rate of 4 megawatts. That's enough power to power 4,000 homes. That's how fast that car is getting energized. And that's why 5 minutes is enough for charging for 500, 600, 700 miles of travel. The convenience of that kind of mobility for the developed world, because we expect that. I get that from my car. I'm not going to be very excited about a car that is more expensive or the same cost. It only goes a third of the distance. And it takes 10 times as long to recharge as a product. The developed world is picky because it's used to good products and good services. Not to mention the cost per mile and what have you. So the fundamental problem of electric vehicles today for the developed world is energy density of the battery, cost of the vehicle, mainly from the battery, and charge time. Now, the battery contains 1% of the energy that the same size fuel tank could. Of course, the electric motor, it's very efficient, by the way. 90% of the energy that goes into the battery comes out, just like 100% of gas that goes into the tank comes out. An electric motor is 4 times as efficient as internal combustion engine. I don't need to sing to the choir. There are internal combustion engine experts in here. I took the efficiency of the engine to be 20%, and I think I'm being kind. Not to mention the fact that the operating point is not stationary. It travels through the power versus RPM plane, and it's not always in the best place. Electric motor is 88, 90% efficient, again, depending on the operating point. The electric motor is 4 times as efficient as the combustion engine. So that makes the 1% fuel tank to appear like a 4% fuel tank. 4% to 100%, we're not there. These are the fundamental problems of technical calculation. Why is one motivated to do this simple arithmetic? Because you don't go with the trends and fashion of the day, nor do you drink your own Kool-Aid of saying something to others and then believing it yourself without the technical foundations. Now, the fact of the matter is, so those are fundamental reasons why electric vehicles are not and will never be as good as conventional internal combustion engine vehicles for the developed world, for the 10%. And that fact, that's theory. And what about practice? Over 20 years, they haven't penetrated the market in the US and Europe that much. Their penetration does not follow the model of a successful product penetration. Example, smartphones were introduced 10, 12 years ago at 10 times the cost of conventional cell phones. but they are so much better. They do so much that without second thought, within 10 years, it completely penetrated and made cell phones obsolete. My beloved Motorola flip cell phone, which I had, which made this beautiful clicking sound that like the Marlboro Man lighter, you know, it just the sound of it makes you want to smoke. And the sound of this flip up cell phone makes you want to make a call. It was just so cool. I still have it because of nostalgia. Someday it may be even more than that. A good product, regardless of cost, over 10 years in the developed world will penetrate, will make its presence eminent and obvious. This is not happening to electric vehicles, and there's a reason for that, as we talk. And this is the picture. You can look at the penetration in terms of numbers of electric vehicles and hybrid vehicles. I don't know how much time I have, but I think I'm getting carried away with myself here. How much? A few minutes? Marvelous. I'm finished with the introduction. Okay. Well, the other side of this is, of course, electric vehicles are not emission free. I don't care if nothing comes out of the tailpipe. It comes out of the power plant, which is 80% or more hydrocarbon fuel power plants in the developed world. And there are issues of heavy metal poisoning and a lot of other issues about excavation of or purification of lithium and other elements that are used for batteries. So here's a quick calculation to give you the idea of, I mean, this is stuff that an undergraduate can do, even a high schooler can do. The fuel to electricity efficiency of a modern power plant is at best 45%. The transmission lines are about 93% efficient. Batteries, round trip energy in and out is about 80% efficient. You multiply all those things together from fuel in the power plant to the battery, energy out of the battery, or let's say the electric motor is 80%. So from fuel to wheel, the efficiency is 27%. Electric vehicles are 27% efficient based on this very topside calculation. Conventional vehicles are about 20% efficient. So we're talking about 7% improvement if everything is really, really going well. 100% penetration saves 7%. All right. Am I really poo-pooing electric vehicles? No. We have to find out where they apply. And they apply as a perfect solution for the 90% problem. The problem of the developing world that needs small vehicles with mobility of no more than 40 to 100 miles and low cost that they can afford. Build me a rickshaw, electric rickshaw for India that travels 40 miles a day and then it has to be charged at night from the grid and costs $2,000. That could penetrate and conquer the market of India. I don't have enough time to give you a lot of anecdotal examples and counterexamples, but this week I read that's exactly what's happening. And I sent it to my graduate students in my hybrid electric vehicle class while I was in the UK, because I read it on the news in the UK. India is building electric rickshaws at less than $2,000. That a typical family in India with an average income of $2,400, I'm not sure if that's annual or monthly, I think it's annual probably, can afford to do it. They can afford to buy it. That's a huge reduction in emissions on the street, toxic emissions. Yes, it concentrates the energy in the power plants, and still it's hydrocarbon and based power plants. But now you have an opportunity to go solar or do something in a country like India. Same thing is true about China. We're talking about more than half of the world population right there. Indians don't need 400 miles to compete with conventional vehicles for a day's drive. I need that because I live in Texas. And just to go to the grocery store, maybe a 30-mile trip, on a weekend trip to go and catch a couple of fish is a 500-mile trip for me. And I think nothing of it. Not in India. It's impossible, culturally and physically. And here's another example of appropriate technology for the developing world, which I read, and this is done spontaneously. The country of Bhutan, which is a very mountainous country north of India, has enormous amounts of hydropower resources. And the government now is legislating that there should be no internal combustion engine vehicles in the country of Bhutan. They should all go electric, charged from the grid, which is energized by hydropower, which means indirectly solar power. But they're going to do it in a non-dictatorial way. They're going to do the government fleets first, then they're going to enforce it on taxis. And when the penetration begins to happen, eventually all the other cars will cycle out and people buy electric vehicles. As an example, the last line, the cost of fuel for a typical taxi in Bhutan will drop daily from $13 to 16 cents. So this is good technology appropriate with sound business practices. And revolutionary here, this is actually from an enlightened government. Good case studies. And so what kind of vehicles should we drive in America and in the West or in the developing world? Well, it should be highly efficient internal combustion engine vehicles for the foreseeable future, because that can happen instantly. People will buy a better car, even if it's more expensive. I have to page through these things very quickly, but just to show you a couple of things. I'm talking about so here's what I consider a good car for the West, for Americans and the British. Better performance, better fuel economy, and no more expensive. That's a car that you prefer to the car you have. A car that costs more and gives you, feel-good stories is yet another Maserati for feel-good things. Anyway, you can take this is an example. In fact, a Chinese student of mine did this for his PhD and surprised me until he justified it. You can take a full-size engine, a conventional car, and he tried to figure out what is the amount of hybridization or electrification of this powertrain that will give you all the benefits of fuel savings in the form of hybrid vehicles. And he did those studies, but the number of kilowatts of hybridization for different sized vehicles and different drive cycles, different drive scenarios. Of course, they're standardized because you have to compare apples and apples. And consistently for a medium weight vehicle or light vehicle, medium weight vehicles and heavy vehicles, all you need is 10 to 25 kilowatts of electrification. You need a 25 kilowatt electric motor, power electronics that goes with it, and 25 kilowatts of battery. That's about 4 or 5, 6 lead acid batteries. No lithium ion, no advanced polluting materials and what have you. And I asked him, why is this happening? And the answer was disarmingly simple, but the fact of the matter is that 25 kilowatts of electrification cuts out the dirtiest part of the operation of internal combustion engine, which is the low end of speed versus power. When engines run at low speed, that's when they start and stop, or go slowly. They are very inefficient, very polluting. And by the way, they're very low performance. A Maserati becomes a Maserati when the engine RPM goes to 6,000 RPM. That doesn't happen immediately. From 0 to 6,000 RPM is a big fraction of a second or two, and this is a whimper. not electric vehicles. Electric vehicles give you all of their oomph from standstill. So in fact, this car will have more pep than a high performance car of the same size engine. So for those reasons, and for the fact that it can recoup most of the regenerative energy of braking, recovering the kinetic energy of the vehicle back into the battery. 25 kilo, this is a typical drive cycle. I don't remember which one it is, both in acceleration, the top, the first quadrant, if you will, and the bottom, the regeneration. All of that can be contained in a stop and go situation in the city of New York or what have you, within the electrified propulsion. It's really amazing. So it is an electric vehicle if you want, if you're just stopping and going, being a taxi, being a last mile service oriented operation, you know, stopping and checking parking meters and ticketing people, or security circulation and what have you. So 25 kilowatts of electrification module fits all the cars, makes them significantly better. And you'll see some of the examples, and it's maybe $3,000 to $5,000 cost increment on a conventional car, a better car virtually at cost parity, and by the way, it's good for the environment. I'm not saying do this. This is an example of good engineering, motivated by high-minded, right definition of the problem. In fact, this car, if you put this in Toyota Prius, which is not which is unfortunately came out of the optimization techniques of our book, and they acknowledged it, that they say this is the best way to build hybrid vehicles. It's called optimized hybridization, reduces the size of the engine, increases the electrification, the cost goes up, the payback, if you use our full-size engine and 25 kilowatts of electrification, the cost of the cost increment is $6,400, payback is 45,000 miles at some assumed price of electricity, of gasoline. And Prius itself, compared to its conventional counterpart, takes 76,000 miles to break even in the cost differential. Performance, or rather fuel economy, our full-size engine, light or mild hybridization gives you 49.9 miles per gallon. Prius itself gives 55 miles per gallon. All right, we need to wrap it up, so we'll do it this way. To summarize everything I said for the developed world, this is lifetime CO2 emissions of various automobile technologies. Let's start at the bottom with the conventional automobiles, the ones that you and I buy in this country, in the US. It produces about 47 tons of CO2 over its lifetime. Electric vehicles produce about half of that because of the configuration of energy generation from electricity generation from hydrocarbon fuels. And half of that is associated with the manufacturing of the battery in the car. We can have cars, advanced hybrid techniques, some of it being developed in my group, plug-in hybrids of different kinds and hybrids of different kinds, which are as good or better in terms of their lifetime emissions. And they don't suffer the penalties of a battery-dominant power plant, because their charge time is at 4 megawatts. You put fuel in it. And the range and the performance and everything else. And under certain conditions, they actually emit less in their lifetime with the present configuration of electric power generation in the West. And it ain't going to change. Sorry, I'm beginning to talk Texan. It is not going to change in the next 30 years. Well, 30 years of bad behavior is game over. You know, the glaciers and the melting and water rising and unstable atmospherics and so on. Anyway, to put it another way, lifetime emission. Let's go, instead of numbers, let's go on the basis of normalization. If we take internal combustion, that's the last column here. No, it's the this column, lifetime emissions. If we take the conventional car to be 100%, the currently available typical electric vehicle like Chevrolet Bolt is 42% lifetime emissions. But these other advanced hybridizations, without loss of service, cost, or performance, can be in the same league or even smaller in terms of emissions. So I think I'll stop with that. You can turn this around in different ways. So appropriate technology for the developed world, appropriate technology for the developing world. Let's get in there and bring humanity to a high level, acceptable level of civilization, economy, dignity. So it's a brotherly thing to do. If you want to be nice to the planet, be nice to your brother. Not your brother in America or in UK, but in Uganda. I have relatives in Uganda. That's why I use that as an example. Sorry, let me say, put one last gig in there to really offend everyone. If all of the vehicles in the United States of America, which is one of the largest concentrations of vehicles in the world, if all of them immediately go zero carbon emission, I mean, really carbon free, its impact on global warming over 50 years is 1/40th of 1 degree Celsius. That's not even an eminent problem to solve. I rest my case.